In sciencey we do best. Miss C helps you pass the test. Whee!
Hello and welcome to the How To series of science videos with me, Miss C. In these videos, we will tackle the topics which at the moment make your brain hurt and make them less painful. This is the second video looking at how to solve problems involving gases. In the last video, we revisited the concept of molar gas volume, which states that at the same temperature and pressure, equal numbers of moles of any gas will occupy the same volume. At RTP, 1 mole of gas occupies a volume of 24 decimeters cubed. So specifically in this video, we're going to look at how we can apply an equation known as the ideal gas equation to questions which involve gases. Now, the ideal gas equation shows the relationship between all the variables which we need to consider when we're looking at gases in chemical reactions. So PV equals nRT. I can hear a song already about that one. I think I'll have to go and make one. So P stands for pressure, and that's measured in Pascal. We've got T for temperature, which is measured in Kelvin. We've got V for volume, which is measured in meters cubed. And we've got N, which represents the number of moles. And then we've got R, which represents the gas constant. Now, if any of you are going to go on and do IB or A-level chemistry, you will learn so much more about how this equation is actually used in real life. So when it comes to questions involving the use of the ideal gas equation, how do we do it? Well, you actually use the ideal gas equation when you've got questions which involve reaction conditions which are not standard ones. Room temperature and pressure, remember, are 20 degrees C and 1 atmosphere. And we can do this using 3 simple steps. Convert the temperature to Kelvin, you convert the pressure to standard units, and then you apply the ideal gas equation. So you know that I'm not pulling your leg. Let's have a look at a worked example. Calculate the volume of hydrogen collected from a reaction conducted at 22 degrees C and a temperature of 1.12 atmospheres. How do we do that? Just like always, we follow the steps. So, step 1, convert the temperature to Kelvin. And remember, when you're going from degrees Celsius to degrees Kelvin, you just add 273. Then we convert the pressure into standard units. So we need to multiply the value in atmospheres by 1.103 times 10 to the 5, and that gives us our answer in Pascal. And then lastly, we apply the ideal gas equation. So that means we just substitute our values into the equation. Then we need to rearrange the equation to make the volume the subject. And when we've done that, we will have calculated an answer of 3.69 times 10 to the minus 4 meters cubed. And that, as a number that we would more be able to process, is 369 centimetres cubed. Not as tricky as you thought. Just to further prove how easy this is, let's look at another worked example. Calculate the volume in metres cubed of 0.0268 moles of nitrogen dioxide gas at 293 degrees C and 100 kilopascals. We just follow the same process to find out the volume. So firstly, we convert temperature into Kelvin. Then we convert pressure into standard units. And this time, remember, kilo is the prefix for 1,000. So all we need to do is multiply 100 by 1,000 and we get our value in pascals. And then all we do is substitute our values into the ideal gas equation. Again, because we're being asked to calculate the volume, we rearrange the equation to make volume the subject. And when we do that, we end up with a value of 0.00126 metres cubed. Easy peasy. So let's have a look at another worked example. So we've got the balance symbol equation here, and you can see that the products in this reaction are both gases. And it says the question, two gases produced occupied a volume of 5,000 centimetres cubed at a pressure of 100 kilopascals and a temperature of 298 K. Calculate the mass of boron oxide that reacted. So now we've not been asked to find a volume, but the mass of one of the reactants. And guess what? We can do this using the ideal gas equation. So we follow the steps. Firstly, convert the temperature to Kelvin. We don't have to do that because the temperature was already given to us in Kelvin. Convert the pressure to standard units. So we do that. So you just times the 100 kilopascals by 1,000 to get the value in pascals. And then we apply all our data to the ideal gas equation. And this time we've been asked to calculate mass. And in order for us to calculate mass, we need to work out the number of moles of gas produced first. So we rearrange the equation, we make moles the subject, we pop our numbers in the calculator, and we get 0.202 moles of gas produced. So we're nearly there. Now, we've got to use the balance symbol equation to look at the mole ratio. And we can see that the reaction produces a total of 5 moles of gas. And we've just worked out that that is 0.202 moles. If we look at the mole ratio, we have a ratio of 1 to 5 boron oxide to the two gases that are produced, boron trichloride and carbon monoxide. So we need to divide the number of moles by 5 because of this 1 to 5 ratio. And when we do that, we end up with a value of 0.404 moles of boron oxide. Now, if you remember from an earlier video, it's very easy to convert moles into mass. All you have to do is multiply the number of moles by the formula mass for that substance. So we can use our periodic table to calculate the formula mass for the boron oxide, which comes to 69.6. So all we do is multiply the number of moles of boron oxide by its formula mass to find the mass, which ends up being 2.81 grams. Woohoo! You did it! Awesome. I hope you found this video useful. If you have, please give it a thumbs up and hit subscribe so you'll be notified when more videos are added. If there are any other calculations in bio, chem or physics which make your head hurt, please add them to the comments box and you may see your request turned into a video very soon.
Helps you pass the test. Whee!